In this session, we are going to learn about the concept of query processing. Okay, what is query processing? I say query processing is the list of activities that are performed to obtain the required tuples that satisfy a given query. Okay, so you can think of it as I have a black box over here. Okay, my query goes in from here and out comes the result, okay, or set of tuples if it is a relational database. Okay, and this entire process is known as query processing. Okay, now let's look at the query processing process. Okay, the steps involved in a query processing procedure. Okay, so I have here a diagram which is going to tell us what are the steps that are involved in a query processing process are. Okay, so this is my diagram. Okay, we have over here three basic units that are being used to process a given query. I have a parser and translator, I have an optimizer, and I have an evaluation engine. Okay, so we are going to look at them one by one. Okay, first let me start with parser and translator. Okay, I'll write it over here, parser and translator. What does it do? Parser and translator, first it is going to check if you have written the query in correct syntax. Okay, so if you have something like select employee name from employee having name is equal to ABC. Okay, then obviously you can see we cannot use having over here, we should have used where. So my parser and translator is going to say that this query is invalid, the syntax is wrong, and it won't be processed. Okay, so the first function of my parser and translator is to check for syntax. Okay, it checks for syntax, then it checks for schema elements. Okay, what do we mean by this? I say if I have query like this, select employee dot, let's say employee dot Gmail account or Gmail username, okay, from employees. Okay, and I realize that Gmail username is not a valid attribute of employees. Okay, employees does not have Gmail username stored. So what is going to say? It's going to say such a schema element does not exist and my query won't be processed. So the next thing is all the elements. So what are the elements over here? Element is the relation employee, element is the attribute being referred. All these elements should be part of the schema definition. So my parser and translator checks for that. Okay, and finally what it does, it converts the query into relational algebra expression. Okay, into relational algebra expression. Okay, so these are the roles of my parser and translator. Now next we are going to come to optimizer. my optimizer, let's see what that it is going to do. I have my optimizer over here. Okay, optimizer basically finds the best way or the best plan to evaluate a relational algebra. Just let's suppose I want to find out the names of the people and their salaries who have salaries greater than 50,000. So what would be my SQL expression for that? It would be something like this: select employee dot name, comma, employee dot salary from where? From the employee table where salary is greater than 50,000. Okay, so this is my SQL expression. So first what I can do is I can convert it into a relational algebra expression. Okay, so how can I convert it into a relational algebra expression? I can do something like this. What I can do is I can project employee dot name, comma, employee dot salary by first selecting only those tuples which have salary greater than 50,000. Okay, from where? From my employee table. Just understand over here, there is one more way to convert this SQL expression into a relational algebra expression. I can also write something like this. I can first project employee name and employee salary. Okay, from where? From my employee table, and then I can select the tuples which have salary greater than 50,000. Okay, so this is another way to do this query. Okay, so what my optimizer does is first is, what was the first unit? We had parser and translator. Let's suppose my parser and translator gives me this query. So my optimizer first is going to find all equivalent queries, all equivalent relational algebra expressions, all equivalent relational algebra expressions. This is the first role of my optimizer. After that, it is going to find the best relational algebra expression which it thinks would find the result in minimum amount of time or having the least cost. Cost could be in factors of CPU cycles, in factors of block accesses, in factors of time spent. Okay, so we are basically talking about cost and not just time over here. So what this is going to do next is it is going to find the expression with least cost. Okay, so what it does for this is, just understand, our every operation over here, like we have projection operation and we have selection operation, right? These all operations can be performed with the help of different algorithms. Okay, so let's suppose I assume that this is the way to do my query. So how would I tell my next unit that you should create a evaluation plan? So my optimizer is going to create a query evaluation plan which is going to tell me what is the relational algebra expression that I'm supposed to going to use and what are the algorithms that are being applied to execute that relational algebra expression. We specify this in the form of an evaluation plan or as a operator tree. Okay, so what I can do over here is I have this relational algebra expression. I can specify it like this. Let's suppose I have my employee table. Okay, employee table. From this employee table, I first, what do? I project, or rather select employees having salary greater than how much? Greater than 50,000. Okay, from the employee table. Okay, and after doing this, what I am supposed to do? I am supposed to project the employee name, or let me just say project name comma salary from employee. Okay, actually we don't even need this because you're already saying that you're working on the employee table right now, correct? So what this is my operator tree. I call this representation as operator tree or a query tree. Okay, now my optimizer is going to find the best algorithm to execute this relational algebra expression. So when I specify the algorithms as well in my operator tree, I get an evaluation plan. Okay, so let me just copy this thing over here, copy, and I say paste. Okay, so after I have found out the cost of all such query trees, I decide that this particular relational algebra with this particular algorithm is giving me the least cost. So I represent this in an query evaluation plan. So what I am going to say? I am going to say for selection you use index A and then use algorithm B. Okay, and after that, in order to do the projection, you use algorithm C. Okay, so this is my plan. Plan has the expression as well as the algorithm to reach to the set of results. I call this my query evaluation plan. Okay, so the output of my optimizer is the query evaluation plan. And how do I make decisions regarding the cost of a query evaluation plan? One particular query evaluation plan, I use this statistics. Statistics contains information about relations like what is the size of relation. Okay, let's suppose I use a brute force method to search a particular condition. In that case, I would have to refer every particular record. So my cost would be the size of relation. If it is, let's suppose 10,000 records, so I would have to see 10,000 records, and that would be my cost. Then it would have the number of blocks being used. Okay, number of blocks being used to store the relation. It could have number of records in the relation. Okay, does it have an index or not? Okay, all such information is stored in statistics, which is being used to arrive at a particular cost. Okay, So after I am done with getting a query evaluation plan, I reach to the final evaluation engine part of the process, and query evaluation engine is going to evaluate the above plan, okay, evaluate the above plan and get the results, okay, and it is going to use the algorithms which are mentioned in the query evaluation plan to do the evaluation, right? Look, query evaluation plan is directly accessing data over here. So once you give a plan to the query evaluation engine, it is going to access the data with the particular means specified by the algorithm, and we get the output over here. Now let's look at the measures of query cost, okay. What do I take into account while calculating the cost of the query, okay? So I have over here the following basic measures. I want to see the disk accesses that I've made, that is included into the cost. I want to see how many CPU cycles I have consumed, how much time CPU has taken to evaluate this query, okay. And finally I am going to see the transit time, okay, transit time in network. But primarily we are concerned with the disk accesses only. Why? Because CPU cost is first of all difficult to calculate, okay, and secondly, the CPU speed is normally increasing at a much faster pace than the disk speed. So with reference to the disk cost, CPU cycle cost is relatively low, okay. So I'm just going to write CPU cost relatively lower than disk cost, okay. And what about transit time in network? Why this is not taken into account most of the times? Because the transit time in network is primarily concerned with distributed or parallel systems, okay. So in distributed or parallel systems, what happens is I have a site A over here which is having some relation, and I have a site B over here which is executing the query. So what happens is site A ships the records to site B, and here we evaluate the query. So this is only applicable for distributed network. So I just for the time being neglect this cost, okay. So my primary measure is the time spent in disk accesses. So now let's take a look at what are the subcategories of cost inside the disk access cost, okay. I'm just going to write disk access cost. So within disk access cost, we have submeasures like the number of seeks that I have to make, okay, to reach to a particular block, okay, number of seeks, and next is the number of blocks that I am going to read, number of blocks read, and next is number of blocks written, okay. Just keep in mind that seek cost is going to be different for random IO, right? And it is going to be different for sequential IO, okay? So I have to take this into account as well. If I have to go to a particular block in a sequential manner, then the cost is going to be higher as compared to if I can reach to a particular block randomly. Similarly, my cost for reading a block and writing a block would be different. Okay, normally the cost for writing is much greater than cost of reading. Why? Because while writing I have to double check, I have to read what I have written to ensure that it has been written properly. Okay, so even that has to be taken into account. So how do I calculate cost over here? My cost would be, let's suppose this is n, then cost would be n into average seek time. Okay, similarly over here my cost is, let's suppose number of blocks read is n, then cost is n into average block read cost. Okay, cost or time. Similarly for here the cost is n, where n is the number of blocks written, into average write cost. Okay, so this was about the various cost factors that I have to take into account. For real-time systems, we take all these factors into account. We differentiate between IO and random. We differentiate between read and write. Okay, because real-time systems is primarily based on response time, and I have to minimize response time at any cost. Okay, also the buffer size that we have in the CPU plays an important role over here. So if my buffer is large, I am going to be able to do large amount of processing in the main memory itself. So my real-time systems also are going to look into the size of memory buffer. Okay, but primarily over here we are going to see only the blocks read and blocks written costs. Now we are going to look at algorithms for relational algebra operators. Okay, we already told while explaining the optimizer concept that every operation can be performed in different manner using different algorithms. So now we are going to study those algorithms. Algorithm for relational algebra operators. Okay, first we are going to look at the selection operator. Okay, selection operator can use two type of algorithms. First is the file scan and second is the index scan. Okay, in file scan what do? We read the file one block at a time. Okay, because we do not know where a particular record may lie. So that is file scan. You can think of it as similar to sequential IO. Okay, and index based scan would be you directly go to the particular record using the index. You can think of this as random IO. Okay, so now first look at file scan based algorithms. Okay, the first algorithm we are going to look at is called as A1. Okay, I'll write it as A1 or linear search. Okay, so let's suppose I have a condition over here theta which says find salary equal to 50,000. Okay, so what I'm going to do over here in linear search, I am going to look at blocks one by one. Okay, look at blocks one by one sequentially. Okay, and I am going to find that particular record. Okay, I assume my file is sorted, so my average seek cost over here would be, my cost over here is, average cost is BR by 2, where BR is number of block reads. Number of block reads, or BR is the number of blocks in relation. Okay. On an average, I am going to read half the number of blocks, but my worst case cost would be how much? Let's assume my record is in the last block. In that case, I have to read all the records. So that is going to be my worst case cost. It is the most simple algorithm that you can possibly have, right? But the beauty of it is it can be used for any selection condition. Okay, it can be used even when there is no ordering. Okay, there is no, it is not mandatory that you need to have an ordering. In that case, cost is going to be BR. You have to see all the records. Okay, because you cannot be sure that once you reach a value greater than 50,000, you cannot say that the 50,000 record won't exist after that. Okay, because it is randomly placed, all the records are randomly placed, it can be anywhere, and you do not even require indices. Okay, so I say it can be used irrespective of any selection condition, any ordering, or availability of indices. That was my A1 or linear search. The second algorithm I am going to look at is A2 or binary search. Okay, so what is a binary search? Binary search is simple. Let's suppose my file is sorted with respect to the search attribute. Okay, and what I'm going to do is I'm going to look at the blocks where the sorted records are kept. Let's suppose I have 10 blocks in my relation. Okay, so I have 1, 2, 3, tick, 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 going up to 10. Okay, I know these are the 10 blocks where my relation is stored, and these are the ordered set of blocks. Okay, so what I'm going to do is, first I am going to go to the 1 plus 10, let's suppose by 2, I am going to the 5th block, let's suppose, and in the 5th block I am going to test. Okay, let's suppose I have a 5th block over here. In the 5th block I am going to test if I have the record with salary equal to 50,000. Okay, so now in the 5th block, if I have the record, well and good. If I do not have the record, then it means my particular record is somewhere around here between the 5th and the 10th record. So now what I'm going to do, I am going to take the mean of 10 and 5. Okay, and I'm going to search in 7th record. If I find it in the 7th record, it's well and good. Otherwise I would get to know if it is between 7th and 10th or between 5th or 7th. So every time I am able to half the set of possible records, or rather set of possible blocks where my records can lie. Okay, So in this case, my cost is equal to log 2 of BR. BR is the number of records in my relation, plus number of blocks containing records that satisfy the given condition, plus number of blocks containing records with same value. Okay, so it may happen I have found my record in 7th block, but there are many such records and I may also have to read the 8th block to find all such records having salary equal to 50,000. That is why I take plus number of blocks containing records with the same value into my cost factor for binary search. Next we are going to look at index scan based algorithms. Okay, index scan algorithms. But before that, just keep in mind that my binary search can only work with ordered file. Okay, the file has to be ordered with respect to the search attribute. Okay, now the index scan algorithms. First algorithm over here is A3 or primary index on candidate key. Okay, let's suppose I am in need to find a record with a particular search attribute which happens to be the candidate key. Okay, and I have a primary index on this candidate key. So in that case, obviously very easy it is to find a record. We just simply go to the index. Okay, I assume my index is a tree index. Okay, assuming a tree based index. Okay, so in that case I am simply going to traverse the tree, find my key, and from that key I am going to get a pointer to the block where my record could lie. Since this is a candidate key, there can be only one record of this sort. Okay, so what is my cost over here? Cost is in terms of blocks that I am reading. Okay, so the cost is the height of the tree. Okay, let's suppose per level I store the nodes in a block. Okay, so if my tree is something like this, okay, so I am assuming that if I have to, worst case I have to reach till 3rd node, I am going to make 3 blocks accesses, 1st, 2nd and 3rd over here. Okay, this is a worst case estimate over here. And after I have reached to the key, I am going to need one more block access to reach the block where my record is present. So one is for the block containing a record, right? So this is my cost in A3 algorithm, primary index on candidate key. Similarly, I have another algorithm known as A4, which is primary index on non-key. Okay, so if it is non-key, there can be more than one record with same search key value. So in that case, my cost is equal to height of the tree, or let's do it in a different color. My cost is equal to height of the tree plus number of blocks that contain the required search key value. Number of blocks that contain the required search key value. Okay, since this is a primary index, the file would be sorted with respect to this particular key. Okay, so all the blocks would be in consecutive locations. Okay, blocks would be in consecutive locations, right? Now the next algorithm is A5. What is A5? A5 is secondary index. Okay, if I have a secondary index on the search key, then in that case, if the attribute is a key attribute or a candidate key, for key attribute, since there can be only one record with a particular key value, my cost is going to be height of the tree plus one block access to reach that particular record. Okay, however, if my attribute is non-key, okay, then I can have many values or many records with the same value, and now my cost becomes very high, because my cost is height of the tree plus number of records retrieved. Just understand over here, the cost is height of the tree plus number of records retrieved for A5, and for A4 it is number of blocks retrieved. Okay, and here I have number of records retrieved. Why? Because here I have a primary index and all the blocks having similar, or rather all the records having same value would lie in contiguous blocks. While this is a secondary index, it is not sorted with respect to this particular attribute whose value is being searched, so the records can lie anywhere. They can, in the worst condition, every record can lie in a separate block. Okay, in that case, for each record fetch I have to make a block read. Now we are going to look at algorithms in which we have comparison condition. Okay, I'm going to write over here selection with comparisons. Okay, comparisons. What could be comparisons? Comparisons could be of attribute value greater than equal to a particular value, or attribute value less than equal to a particular value. Okay, so first we are going to look at primary index based approach. So next algorithm is A6, which is primary index for comparison. Okay, so here what do we do? A6, if I have to make a selection A greater than equal to V from my relation R, okay, what I'm going to do is I'm going to find the index record where A is equal to V from index. Okay, and after that I am going to, first step is this, second step is I am going to sequentially read the file till the end. Okay, read the file till the end. Okay, since I am looking at records A greater than equal to V, it is my primary index, my file is sorted with respect to this particular attribute value. So once I find the record having A equal to V, all the records ahead of it would have value greater than V. Okay, and for this selection, or rather this selection A less than equal to V from record, what we are going to do is we are not going to use an index, we are going to start reading the file from the beginning. Okay, we won't use an index. I'm just going to write here that index not required. Okay, from here, after starting from the beginning, I am going to sequentially read every record sequentially until I find the record with value, until record with value equal to v. Okay, right? So that is how I use my A6 algorithm on a primary index. Okay, now let's look at my A7 algorithm, which uses a secondary index for comparison. Okay, here, since this is a secondary index, my file is not sorted. Okay, so for a greater than equal to v, what I am going to do is I am going to first find the index entry with a equal to v, and then I am going to read and follow sequential index entries from there. Read and follow next index entries that follow. Entries until the end. Okay, or rather read and follow subsequent index entries. It is a better word to explain what is exactly happening. Okay, I'm going to see the next index entry, and from that entry I'm going to find the pointer which is going to take me to the block where next record is present. Just understand over here. Here I am reading the file, while over here I am reading the index entries. So that is the difference between A6 and A7. Okay, and for the next case where I have a less than equal to v, what I am going to do in that case, I am going to start reading index entries starting from the beginning until I get to v. Okay, so let's suppose I have a tree something like this. Okay, so obviously I know that my records are present in the leaf nodes, so I am going to start searching like this. Okay, at the leaf nodes. Okay, so what is the procedure? Procedure is start from the leaf nodes. Okay, and leaf nodes of index. Okay, and keep following pointers until you get an index entry with value equal to v, until an index entry with value equal to v. Okay, so that is how in A7 I find my particular set of records. Just remember that A7 is a secondary index, therefore it can be very costly. For every pointer it may happen that I have to make a new block access. Okay, in A6 we follow the file, while in A6 we sequentially read the entries in file, while in A7 we sequentially read the entries in index. Now we are going to look at selections with complex conditions. Okay, what do we mean by complex conditions? It means that we have more than one condition on a specific attribute, or conditions on more than one attribute. Okay, so I'm just going to write it down over here. Complex selections. Okay, my complex selections is going to be of the type theta1 and theta2 and theta3, right? Or it could be of the type theta1 or theta2 or theta3. So for example, I want to find the employees who have, let's suppose, salary greater than 50,000, okay, who are living in city LA, okay, and who are working in department finance, right? So here my theta1 is this particular condition, theta2 is this condition, and theta3 is this condition. Okay, so now let's look at the algorithms for such type of selections. AND is called as conjunctions, okay, and OR is called as disjunctions. Okay, so first I am going to tell you algorithms for conjunctions over here. I'll write over here conjunctions and we'll begin with algorithms for conjunctions. My first algorithm is A8. Okay, A8 is selection using one index. Okay, so how do we proceed over here? Let's suppose I have three conditions as already mentioned. I have theta1, I have theta2, I have theta3. Okay, now for each of these conditions I am going to find an algorithm which has the least cost. Okay, so let's suppose for theta1 I calculate the fact that A5 has least cost. Okay, similarly theta2 I find out that A3 has least cost. Similarly for theta3 I realize that A2 has the least cost. Okay, just understand, at this point I am only calculating costs, I am not calculating the tuples. Okay, after I have done this for all the thetas, okay, for all theta I, okay, once I have done this for every condition, I find the condition which has the least cost. Okay, so let's suppose my theta1 costs me 50 units, my theta2 costs me 30 units, and my theta3 costs me, let's suppose, 70 units. Okay, so out of these I realize that my theta2 has the least cost. Okay, so now I calculate the tuples based on condition theta2. Okay, so calculate tuples for theta2. Once I have done that, the next step is to, from among the tuples which satisfy theta2, find the tuples which satisfy theta1 and theta3. Okay, and this is the result. Since what am I supposed to find out? Theta1 and theta2 and theta3. At this instant I have theta1 tuples. From this I have, at this instant I have theta2 tuples, and from that I am taking the tuples which have theta1 and theta3 also. So technically I am calculating the tuples which have theta 1 and theta 2 and theta 3. So that was my A8 algorithm. My next algorithm is A9. Okay, A9 is selection using multiple key index. Okay, multiple key index. So let's try to recollect what was a multiple key index. Let's suppose I have a multiple key index on city and salary. So what would be my search key values for here, or rather what is my index entries over there? I would have, let's suppose, salary equal to 50,000 or rather 5,000 and city equal to, let's suppose, Los Angeles. Similarly, I would have salary 5,000, city equal to, let's suppose, Santa Clara. Then I would have, let's suppose, salary 6,000 and city equal to, we'll take Chicago. Similarly, salary 6,000, city equal to LA. Okay, so I'll have such kind of entries in my index record. Okay, this entire field is the search key, and over here I have the pointer. Okay, I have the pointer to records. Over here I have the pointers to records which have city equal to, or let's put a different color over here because this is my main heading. Okay, and I don't have a pointer over here. I'm just going to write out that this is my pointer column. Okay, so where does this point to? This points to all the records where city is equal to LA and salary is equal to 5,000. Okay, so now if I have a conjunctive condition, let's suppose I want to find the records where city is equal to Santa Clara and salary is equal to 5,000, I can simply look into my composite, my multiple key index, and I'll go here, and from this I am going to fetch the records which have salary equal to 5,000 and city is equal to Santa Clara. So this is my A9 algorithm. We use the multiple key index. Obviously such an index has to be available for it to be used, only then A9 is applicable. Okay, now let's look at A10. A10 is conjunctive selection by intersection. Okay, so over here what we do is we calculate individually theta 1 using the best algorithm, theta 2 using the best algorithm for this condition, and theta 3, and let's suppose here I get result set 1, here I get result set 2, and here I get result set 3. After I've got all the relations, or rather all the tuples which satisfy theta 1 and all the relations which satisfy theta 2 and all the tuples which satisfy theta 3, okay, then I take the intersection of each one of them. So I take intersection of RS1, I take intersection of RS2, and I take intersection of RS3. What would this give me? This is going to give me the desired result. Okay, because this has theta 1 condition, this has theta 2 condition, and this has theta 3 condition, right? So if I take an intersection of each one of them together, I am going to get the intersection of theta 1, theta 2 and theta 3, which is my desired set of result. Okay, this is the A10 algorithm. Now we are going to look at disjunction, which is the A11 algorithm. Okay, disjunction A11. A11 is disjunction using union. Okay, disjunction by union. Okay, so what am I supposed to find? I am supposed to find theta 1 or theta 2 or theta 3. Okay, this is my complex search condition or complex select condition. So what am I going to do here? I am going to find theta 1 in the best possible way. I am going to find theta 2 separately in the best possible way. Similarly, separately I am going to find the tuples which satisfy theta 3. Okay, it is similar to A10. Let's suppose here I have result set 1, here I have result set 2, and here I have result set 3. So now if I have to find the disjunction, I am going to take the union of all of them. So RS1 union RS2 union RS3 is going to be my result, my desired tuples which have either theta 1 true or theta 2 true or theta 3 true would be in the union of RS1, RS2 and RS3.